I mentioned that you could use a ruler and a protractor and Snell's law to more convincingly demonstrate the behavior of a converging lens, and I challenged somebody in the class to do so. I still hope I get some responses to that, but here's my rushed attempt. I just drew an arbitrary curve on both sides of the lens, approximately spherical. The smoother that curve is, the better your results will come out, I think. And I drew 1, 2, 3, 4, 5 rays, but I only numbered the top 2 and the bottom 2 because I assumed that since this ray was normally incident, it would just continue on straight forward. And what I did was use Excel, Microsoft Excel, to calculate the refracted angle here based on the incident angle here. I assumed an index of refraction out here of 1 and an index of refraction in the interior of the lens of 1.5. Now, 1.5, that's 3 halves. So when you look at Snell's law, you can expect to see a factor of 3 halves in there, or 2/3 if you're looking at the reciprocal. Once Excel told me what this angle should be, I used the protractor to draw it. So I will quickly demonstrate what I did here. I just eyeballed these rays, making sure that they were all coming in approximately parallel. I placed the crosshairs of the protractor over the point of contact with the lens, and I make sure that, hang on a second. Yeah, I make sure that the horizontal line here is coincident with the incident ray as closely as possible. And as I noted down here, I just eyeballed the normal line. I tried to draw a normal line that was as close as possible to being perpendicular to the tangent at that point. My results may have come out better if I had used a protractor to make sure that the normal line was 90 degrees from the tangent line. But I used the protractor like so to measure this angle. I can take my ruler and lay it alongside the normal line and read off the angle from here. And again, the more care you put into this, the better your results will come out. I determined that ray 1 made an angle of 23 degrees with the normal. Let me go over to Excel now. And I made 4 rows, 1 for each of those numbered rays. Here I entered the angle in degrees that I measured, and I've implemented Snell's law here. This will give me the angle of refraction at that first interface from air to glass. And evidently that should be 15 degrees approximately. Back to the diagram here. So I didn't bother writing that number down because this diagram would have been fairly cluttered. But I then got out my protractor, and this time I align this horizontal line on the protractor with the normal line that I had previously drawn, and I go around the perimeter here and find 15 degrees. You'd put a little dot here. Actually, am I doing this right? Yeah. You'd have to put a little dot at the perimeter of your protractor, and then, as I've done here, maybe you can see no, you can't see, it's too faint. There's a tiny little dot here, and I put my ruler through that dot and through the point of contact and drew this ray, letting it terminate at the other face. So that I made sure that this angle was 15 degrees, which came out of Snell's law. And then you just repeat that procedure here. You'd have to get out your protractor again, measure this angle as carefully as possible. We'll go back to Excel. That's the angle that I'm calling theta 3. So I entered theta 3 here after measuring it. And once again, I use Snell's law to find the refracted angle on the other side. Now be careful, the roles of your 2 indices of refraction, they're reversed for this refraction versus this refraction. So be careful when you're implementing Snell's law. And that 4th angle that spits out, or comes out of the function, that's the angle that I would draw here. I did that all the way down. So what was that? 1, 2, 3, 4, 5, 6, 7, 8 calculations using Snell's law, but it's very quick with Excel. The only thing that takes a little bit of time is measurement with the protractor. And here's how my diagram came out. It was a little disappointing. I also made some mistakes here. It was disappointing because I was hoping that all of these rays would intersect in a single point or close to a single point. If I look at rays 1, 2, and 3, they seem to intersect right about here. That looks pretty good. This ray misses the intersection point by quite a bit, and it may be because I just assumed it was going straight forward. You can tell this is not exactly 90 degrees here. Maybe if I had used a protractor, I would have gotten better results for that ray. Also, this bottom ray, ray number 4, really doesn't pass through the common intersection point of rays 1, 2, and 3. And that may be because that ray is fairly close to the edge. Remember, the rays that obey all these approximations we'll be talking about, those are the paraxial rays. These two rays are fairly close to the axis. This one, not so much. So I'm not sure why this one worked fairly well and this one didn't. But if you were to draw additional rays way down here, you would find that these probably miss the intersection point by an even greater amount. Now, there is error involved in my drawing here because the pen tip has a finite thickness, and there's error associated with using the protractor. So if I had used a really big piece of paper, made this even bigger, stuck with paraxial rays, and made super precise measurements with an even thinner marking tool, maybe, or a pen, maybe these would have come closer to converging at a single point. But this is enough to give you some idea. If you come up with a better diagram, please share.